Thanks for the introduction, and great to be here. Thanks for coming to this session. So I'm gonna introduce Cosmos World Foundation Model Platform that we are building to all of you. So our target is physical AI builders. Physical AI is hard. So the AI cannot just live in your computer. It has to trigger something to interact with the world. And when it interacts with the world, it can cause damage, right? So we believe that it's not responsible to let premature AI going around, and it's not good for your pocket, and we need to do something smarter. So we believe that you have to first train your physical AI digitally high enough before lay it out. And we believe there are two important parts of physical AI, two important AIs to enable physical AI. The first one is the digital twin of the robot. And the model run on the robot is usually called the policy model to trigger the motors. And if you were in general keynote, NVIDIA just announced Goods N1, which is a policy model that is good for humanoid robots. You also need another AI, which is the digital twin of the world. The model is a world simulator. So with this world simulator, you don't need your physical AI to interact with the real world. It can interact with this world simulator to lower your development cost. So here, as Cosmos World Foundation model, so we want to enable all of you to build high-quality world simulators for your physical AI. And there are three main things we include in this Cosmos World Foundation model platform. The first one is pre-trained Cosmos World Foundation models. These are models trained with large-scale open domain videos with all sorts of contents from self-driving car, from human-object interaction, so that the model is generalist, not a lot. The second important component, we call it the post-training script to fine-tune pre-trained or post-train the pre-trained Cosmos Foundation model or Foundation model for your downstream applications. Each physical AI have different sensor setup. Some physical AI has 2 cameras, some has 6 cameras, and some also have LiDAR sensors. So the world perceived by different physical AI are different. We believe this customization is needed. And we want to help you guys, so we're gonna provide this post-training script to help you use the pre-trained Cosmos World Foundation model. The last component is the video data curation pipeline. Videos are very dense, a lot of pixels, a lot of tokens. If you want to build a high-quality model, you have to get a huge amount of videos, even for post-training. And processing those videos are challenging accelerated computing problems. NVIDIA has spent years on building also libraries to help you accelerate the processing of videos. Through this Cosmos Foundation model platform, we put them together, open source them so that you can leverage them for your data processing. So this is the mental picture I have, right? So you have pre-trained World Foundation model in Cosmos, and you're gonna have your own data sets tailored for your own applications. And we're gonna provide you the post-training script to post-train the pre-trained World Foundation model to your downstream applications. It can be a self-driving car, can be a robot arm, can be a robot dog, or a humanoid robot. And I also want to mention this, the NVIDIA 3 computer strategy to help physical AI builders. So we have this DGX large-scale data center class GPU cluster to help you build large-scale foundation model. NVIDIA Cosmos is built on NVIDIA DGX. And with NVIDIA Cosmos paired with Omniverse, you have a powerful simulator. Omniverse provide you 3D conditioning, and Cosmos provide you photorealism and other imagination capability. And Then those models can be distilled to operate on the edge device in NVIDIA HX. All right, so I will start with the last component, the video data curation pipeline. So to build this model, we first need to curate a huge amount of data. So we have gathered about 20 million hours of videos, use standard tokenization, you give you 9,000 trillion tokens, a lot of tokens. And we have been using around 10,000 NVIDIA H100 GPU to build this sequence of Cosmos models. When we curate the data, we curate it very carefully. We want one that's good for physical AI builders. So we have huge amount of driving videos from the dash cams, huge amount of human object interaction videos, natural dynamics to teach AI about how physics works. All sorts of category that we believe is good for physical AI. Of course, through our learning, your feedback, we're gonna iterate the composition, and hopefully we have a better and better pre-trained world foundation model for you guys. And here is our data curation pipeline. So it's open source. It's available in Nemo Curator. So this is just an illustration, right? You have, let's say you have a 1 hour long video. You want to use them to train your physical AI. And that 1 hour long video, most of the time can be very boring, right? So the first thing we do is we divide this 1 hour long video into clips. And this requires transcoding. Decode the video, H264 decoding, and re-encode them into individual clips. Once you have this clip, you need to do filtering to remove the portion of those videos that are not useful, right? So we have set of filters to help you to do that. One is motion filter. If there's no motion in the video, delete it. If the video is poorly captured, very dark, delete it. And then if there are a lot of text on the video, maybe not good for learning the physics of the world, delete it. And we then categorize the video into one of the physical AI category to help us control the proportion to use to train the model. And those videos, we use a vision language model to describe the video so that we can learn more controllable generation that we're gonna use in later. And now we have a huge database of videos. And a lot of video gonna be very similar, and you probably don't want to waste your GPU to train the same stuff. So we do semantic deduplication. What we do is we represent each video as a latent vector, and based on the similarity, we delete some of the redundant ones. And then we do sharding, so videos of the same duration, aspect ratio, resolution are grouped. And this is important for us to maximize the host powers from GPU to do the processing. All right, so now I'm gonna talk about the Cosmos World Foundation models. Earlier I told you we have 3 components, right? The pre-trained one, post-training script, and data curation. In the World Foundation model side, we also have 3. So in CS, 2 months ago, we released the first one, which is we now gonna call it Cosmos Predict. So it's a world simulator based on your current observation and predict the future, right? To think about what's gonna happen in the future based on your current observation. The second one is one that's we show some of the results in CS, and Jensen also showed it earlier in his keynote. We call it Cosmos Transfer. So from one domain to another. The one domain can be synthetic domain, do scene to real, and those synthetic domain can be generated by NVIDIA Omniverse. And the last one is Cosmos Reason. So it's a reasoning model tailored for physical AI. It's not good as Olympiad math or coding, but it was built for the purpose for the robot to survive in the physical world. So we emphasize more on knowing how to interact with the object more than solving math. I'll talk about all of them in this talk. So this is a mental picture. You have 3 models: Cosmos Predict 1, Cosmos Transfer 1, and Cosmos Reason 1. Cosmos Predict 1, world simulator. Based on the current state, predict the future. So this is, or you can call it a world model. So here, x0 to t, let's say our robot use video as a sensory input. This are the S0 to D is the video you have observed so far. And C here is the control signal. It can be a text or robot control signal. Based on what you have seen so far and based on text, what's going to happen next. The output is the future state, the next frame. And this is very useful for several physical AI applications. One is for policy evaluation. Right? Let's say you train a policy model that you want to deploy in the robot. And people who work on AI, they know that usually you have a different variation of the model and many, many checkpoints. Do you know which one you're going to deploy to the physical robot? You're going to try all of them. Some of them might be very bad, like what I showed earlier in the slide. You're going to damage your environment, right? How do you effectively find a few good one before you deploy it, right? So with this world model, you can let your policy interact with the virtual world, and then find from the 1,000 checkpoints, you find the best 10. And then you spend the time, energy, deploy the real robot to see how it goes. And it's also help you, right? So you want to test your robot in kitchen, maybe you have 10 kitchens, but you probably want your robot to work on 1,000 kitchens, right? So with a world simulator, you can generate many, many kitchens to test whether your robot is good enough before release it to your customer's kitchen, right? And also, if this world model is good at predicting the future, it probably can be reconfigured to generate the action toward that future. So it can be serve as a policy model pre-training. And if you have a perfect world simulator, you can actually use a classical mathematical model predictive control to always get the best solution, right? And also you can use this world simulator as data generator, synthetic data generator to train your robot. Okay, so here I'm going to talk about one of the world foundation model we use, which is a diffusion-based video generator. So it's we use a tokenizer, causal tokenizer, which means that the tokenization of the current frame doesn't depend on the future. We use causal because it's how the physics works, right? You don't see the future. And then after that one, we built a standard diffusion transformer architecture, large-scale one. And then we train the diffusion model to remove noise on corrupted token and eventually become a video generator. We built two models, families of different sizes. We start with a 7 billion text-to-word diffusion model. And we also built a 14 billion one, and we found 14 billion one is better than 7 billion one. We start with the text-to-word. We build the model to convert text to the videos, and then we fine-tune it to become video-to-word based on the past video and some commands, some text you generate in the future. So we do that for both of the versions, and we have released both of them. So this is pretty one, right? So past few frames, text prompt, and you generate the future. And this is some of the results. You start with input and then become conditions. So it can help you generate different environments to test your physical AI. And we also include several examples in the paper, and some of them, actually most of them is released today in the form of native Python training script in our updated GitHub website, so you can go and check it out. So we have camera control. So in this scenario, in addition to text prompts, you also take camera trajectory as the input. Now you can use the virtual, you can control camera trajectory to navigate the virtual world. Here's one example. Go front, back, left, and right. Yeah. So you can also use different trajectory. What we did is we find a subset of videos where we can extract the camera poses robustly. And for some driving scenario, it's easier because you have other modality to help you get the camera poses. And we fine-tune Cosmos model condition on this camera trajectory during training. The diffusion model leverages the camera poses to remove the noise. And in the test time, you can use camera poses to control the diffusion model so you can navigate in the virtual world. And this is another example, shopping in the supermarkets. And here in the industrial setting, zoom in to the robots, zoom out, left, and right. Yeah. Okay. And some robots have multiple cameras, like self-driving car. So what you can do is instead of generating one view, you can generate 6 views or 8 views. And we are using transformer, right? So the difference is gonna have more token, more output tokens, and those views, they actually attend to each other. There are other things you need to be considering. We describe all of them in our paper, and we're gonna release this post-training script soon. Yeah, so now you can do multi-view generation based on the text prompts. You can also add the vehicle trajectory. So not just generating 6 views, you also condition the generation on the vehicle trajectory. You might have some data sets already have a vehicle trajectory recorded, so you can post-train the Cosmos model for that purpose. Right, so here you see the red dots indicate the camera trajectory. So this helps you to build a pure deep learning-based driving simulator. Okay, so you can also fine-tune the model instead of take general text prompts, take text instruction you want the robot to do. And here is some example. This is based on 1X robot. So you now put the command, organize books by placing them vertically on a shelf. And each of the instructions give you a future output, the video. Okay. And you can, instead of, in addition to, actually, another way to condition it is to use the numbers, the control signal that you enter to the robot to do the stop. We call it action-based control. So you now put a set of numbers into the diffusion model and generate the future states. Yeah, so here it just specify the camera, the control signal, and the robot arm is doing the thing that you expect it to do. Okay, so this is the Cosmos predict. So now I'm gonna talk about Cosmos transfer. So Cosmos transfer 1 is coming from Cosmos predict 1. So it's a conditional world generator. So you can, the mental picture I have is this. So you have 2 worlds, actually. Sorry, I have a typo here. The first one is world number 1. World number 1, let's say it's Omniverse. Right? Omniverse, you can have some modality observed. One is the depth, one is the segmentation, the other is, let's say, the RGB rendering, right? And through the Cosmos transfer 1, you can map those videos, those modalities into the video that would coming from the real world. So it should be simulation in world number 2. Sorry. Yeah. So this is the Cosmos transfer 1, and let me show you the video the team made. So this is what we did. We start with the Cosmos PT1, which is a diffusion-based transformer-based diffusion model, DIT model. Such a model has multiple transformer blocks, and you guys might be familiar with familiar with the control net. So control net is a popular approach to make diffusion model take spatial control as input, like a segmentation map or edge map. So what we do is we duplicate the first 3 transformer block from the Cosmos predict one as separate branch. And then this separate block is taking the conditional input, right? Can be edge, can be segmentation. And then we do, after the transformer output, block output, we do the linear projection and add that back to the main branch. So this way, the denoising training objective of diffusion model is trained with the condition information, the segmentation, and the model is smart to leverage those segmentation to help remove the noise. This way, we build a path to connect the control signal to the final output. Right, and this is a typical control net, and what we build for Cosmos Predict 1 is multi-control nets, right? Because there are so many modalities and all of them are useful. So we have still the main branch, but we now have M modalities. You can have edge, can be have segmentation, depth, thermal, many different things. You name it, just many, right? And for overland, when it's before it come back, before it's added back to the main branch, you see that W1, W2, Wn here, right? This is the weighting matrices. So we allow the user to control how important you think a particular modality is. And this is pretty handy, right? But for example, in some scenario, you don't want to change the foreground. Your robot is that robot, you don't want it to be changed. Some of the main object you want to keep is the same, but you want more variation for your background. With this one, you can use segmentation and say, oh, whenever it's a foreground object, I need to put strong weight here. But the background, I allow you to go crazy, right? So this is one of the control you get, right? And the way we build the transfer one is we actually first build individual control net separately to make the training problem much easier. You don't need to handle one model of data during training. But during the inference time, we fuse them together. Okay. And this is an example I mentioned earlier. So it actually allows you to do this adaptive spatial temporal multimodal control, right? So here you have a person doing certain activity, and we have the foreground mask. Right? The foreground mask is the human with the object. And we can put strong weight there and ask the model to leverage more on this. This is the blurred visual of the input. So it provides a color cue. So you don't want to change the skin color of the clothes color of the person. And edge give you fine-grained geometry detail you want to keep. And then for the background, we use depth and segmentation. And they just specify the layout, geometry, and semantics, and then you can change. Yeah. All right. So this is one example, and it's another example. And you have seen this for self-driving using HD LiDAR, and for generation. This is another one. Okay, so I'm now going to talk about Cosmos recent one, right? So very quickly, reasoning model is pretty much an LLM that think a lot, right? Before it come out with the answer, you have this chain of thought, thinking to lay out what they are thinking. It's like before you work on something, you write down your plan on the paper, and you might find some mistake, and you can revise your plan, right? So I think this is one of the reasons why reasoning model is better on many tasks. And the field has shown that reasoning model is very good at solving Olympiad math, solving theorem proving and coding. I'm working to help physical AI builders building Cosmos recent one, and I believe physical AI doesn't need to solve Olympiad math or do the coding. So we want to build one that's only good for physical AI tasks. And so we are not for this Okay, we leverage the reasoning capability, but we are not trying to solve Olympiad math or other. We are not trying to build AGI. We want to build something useful to you guys. And there are two sets of capabilities, reasoning capability we've seen is important for physical AI. One we call it physical common sense. The other we call it embodied reasoning. So physical common sense. So we believe that there are three main physical common sense. One is the common sense about space. There's time, and the other is fundamental physics. For space, it can be, we further divided into many categories, right? Space, including the, affordance, environment, relationship. Time, including the action, order, causality, and planning others. Fundamental physics, you have attributes, state, object, permanence, mechanics, electromagnetics, thermodynamics, anti-physics, right? Since that doesn't follow physics. So these are things we believe that physical AI agent should know. And also embodied reasoning. So we believe that these are the important reasoning capability physical AI should have. Be able to process complex sensory input, predict action effects, respect physical constraints, and learn from interactions. And we have a detailed breakdown what we mean by individual ones, embodied reasoning gonna be different for different embodiments, right? For human, right? So processing complex sensory input, a person watch video, learning how to cook something. A robot might rely on LiDAR data to sense the world, so it's gonna be different, but we believe that all the physical AI should have this capability of process complex sensory input in order to survive the physical world. So yeah, so these are the things. Sorry, in the interest of time, you have to go to the paper. But in the end, what you have is a multimodal LLM. So you have input video, you do vision encoder, it projects into the video token, and use LLM to process that. Just now, you do thinking before you provide the final answer. So it's a very standard structure. The key is how you curate the data, those data that I described earlier, those embodied reasoning and the physical AI common sense. And we have a very detailed description how we curate data in the paper. It's up today, so please take a look. Yeah, and what we do is we take a pre-trained multimodal LLM, we do physical AI supervised fine-tuning, and we then do physical AI RLO. Physical AI supervised fine-tuning is pretty much based on the curated data sets. We have some kind of reasoning annotated by human to teach the robot how to reason about particular effects. And physical AI RLO, we use a verifiable reward. The data sets all built based on our analysis of what is important for physical AI. Okay, so we use a verifiable reward. So pretty much you can say it's 1 or 0, verifiable reward. And we use the GRPO algorithm, the group relative policy optimization algorithm popularized by R1. GRPO algorithm is pretty simple. You just group a bunch of outcome together. If you are the only good solution there, you're gonna be weighted a lot. If you have a set of good solutions, it's okay. But when every solution correct, it's probably not a very important sample. It's an easy case, right? Just a way to naturally emphasize more challenging examples. Okay, so this is one of the RL tasks we used to train our Cosmos reason. So we play video and ask the AI to reason is the video play forward or backward. Let me do a quick test here. Is the first video play forward or backward? Yes. How about second video? It's harder, right? And third video. This one should be easier. So we pretty much torture our AI on all kind of tasks. Verifiable reward. You don't need a human annotation. Take a video, play backward, and challenge the model to figure out. And in order to learn how to do that, you have to find the essence of how time works. Yeah. The other test is jigsaw puzzle. So we mix a bunch of video together, and we add the file question. You are given 32 frames, and want you to find 2 other frames. This is coming from the first frame. And the model have to work very hard to understand. So what I'm trying to do here is say that there are many verifiable rewards you can synthetically generate that might help your physical AI to non-stop. Yeah, and this is the result. So here we asked our Cosmos recent one a question. The overall goal is the agent pour milk into the cup. The agent in the video is currently perform one subtask out of many to complete this instruction. For the agent in the video, what is the most possible next immediate subtask? And you see the agent start to think, okay, let's see, and eventually say, oh, but the question is about the immediate next action. Since the milk was just poured, the immediate next action likely to stop pouring and put the bottle away, to create this capability. And here's another, is the video playing backward and forward as the model to reason. And the agent said something very interesting. The amount of pink powder in the container increases while the amount in the buckets decreases. This suggests the action is being undone, so it's a backward, right? And this is also interesting. Based on the vehicle action in the video, what is the most likely immediate action it will take next? So you see, I would guess it probably want to go to the, make a left turn here, right? And the AI start to think. And at some point, it say option A is doing this, option B is doing this, option C is doing this. But then he realized, oh, this might be a trick. Let's double your line here. You're not supposed to make a left turn. And then he refused to give an answer and said the answer is none. Yeah. So these are the kind of capability we want to empower our physical AI. All right, and this some benchmark results. We create a set of benchmarks tailored for physical AI use cases and compared to popular model like Q1, GPT, and O1. And we start with the backbone, the VON, and then do the Cosmos recent one post-training. And you can get better result. And when you do ILO further, and these are a bunch of physical AI, so I don't have time to cover them detail in the paper. Let's go ahead. I want to go to the important part, which is everything is open sourced. So we have released the checkpoints for the Cosmos Predict in CS. Cosmos Transfer 1 is released. Cosmos recent one, we need to do some other paperwork, so it's gonna take some time. But they are out. And the technical content are in detail, described in detail in our papers. Today we published 2 of them. In CS we published 1, so now I have 3 papers, 1 on Cosmos Predict, 1 on Cosmos Transfer, 1 on Cosmos Reason. And we decide to make it better and better, so we're gonna build Cosmos Predict 2, Transfer 2, Reason 2, and Predict 3, keep building until you guys don't need us. And want to say that Transfer 1 is coming from Predict 1, and we want to make all of them better and faster. And we actually believe that synthetic data generation can help reasoning. We also believe that reasoning can become great critics to help improve the video. Right? So you have one real video, one fake video, and ask the model to reason why it's a fake video. Yeah. Okay, so again, we have 3 main components. We are releasing native PyTorch scripts for people who just want to use native PyTorch. We hear you. It's out today. And we're going to put some more and accelerate our deployment. And thank you.